So my fascination with logic started with a profound shock. The way I dreamt of science and mathematics is that one day, after hard work, we can eventually devise a theory of everything, or at least a theory which contains every mathematical truth. So you can understand my deep frustration when I learned that in the 1930s, a logician called Kurt Gödel showed that my dream is impossible. That is, there cannot be, for purely logical reasons, a theory which proves every mathematical truth. And in the first part of this talk, I would like to tell you a bit more how Gödel proved his groundbreaking discovery. And then in the second part, I will speak about my own research, in which I argue that in order to fully understand its philosophical consequences, further generalizations of Gödel's theorems are required. Okay, and Gödel's result is fundamentally concerned with the limitations of mathematical proof. So what is a proof? And we start by laying down axioms, which capture basic, undeniable facts about numbers or about geometrical objects. So for example, we may have an axiom which says that the order doesn't matter when we add natural numbers. So for instance, we have x plus y is just the same as y plus x for any numbers x and y. We may have another axiom which says that 0 is the smallest natural number, and so on. And then we have logical rules, which allow us to derive new mathematical statements from these axioms in a certain regimented way, right? So you can think of proofs as complex objects which are built together from these axioms. And as a result, proofs provide us with a rigorous method to explain why mathematical statements about numbers, about geometry, are true with total certainty. And since ancient Greece, it has been the main goal of mathematicians to either prove or disprove each mathematical statement. And so now the outrageous thing Gödel did is to show that this goal is impossible. That means that we can actually come up with a true sentence which we cannot prove. And even worse, Gödel showed that mathematics cannot prove its own consistency. So it's impossible to mathematically establish that there are no contradictions in mathematics. So how did Gödel do that? And let me start by briefly introducing the citizens of the world of mathematics. So we have numbers as the paradigmatic objects of mathematics. We have geometric shapes, some of which will be familiar to you. We have functions and operations, and we have sets of numbers and other mathematical objects. And mathematicians typically study the properties of these objects. So for example, we can formulate and prove the claim that there is no odd number which is divisible by 2. And this is a claim about all the numbers in our mathematical universe. But now Gödel was interested in the following claim. There is no proof which derives a contradiction, such as the equation 0 equals 1. And now this claim is about proofs which we use to explain certain features about mathematical objects, but which are not mathematical objects themselves, right? So as I illustrate in this slide, proofs, at least before the time of Gödel, were not part of the realm of mathematics. And so in order to make his claim precise, Gödel had to come up with a new way of introducing proofs as objects of the world of mathematics. And he did that by producing what we call today a Gödel coding. And roughly you can think of a Gödel coding just as a machine which transforms all kinds of objects, such as apples and bananas, into numbers. And in particular, this machine translates mathematical sentences and proofs into their code numbers, and thereby allowing us to express complex mathematical ideas by single numbers. And while in the 30s, it took a genius like Gödel to come up with such an idea, today, Gödel codings are part of our daily life. And I mean, we just heard a nice talk where this was really a strong feature. And think, for example, of your Word document, which is represented by a long sequence of zeros and ones inside your computer, and where all your edits and copy and paste manipulations correspond to certain number theoretical operations on these binary sequences. And similarly, since now each mathematical statement and proof has its own code number, we can use numbers to speak about proofs and mathematical formulas inside mathematics. So in other words, we can now use mathematics to speak about itself. And Gödel used this method to formulate the following sentence: this sentence is unprovable, in purely number theoretical terms. And here we meet Gödel with this sentence, but in Gödel's defense, the handwriting is mine. And in mathematics, sentences are either true or false. Okay, so let me now ask you, let's do a little experiment. If you think this sentence is true, then please give me a thumbs up. And if you think the sentence is false, then please give me a thumbs down. You can either pick the emoticon or you just show your thumb into the camera. Okay, great. I see we have a lot of logicians here. That's excellent. Nice. Okay, you're all very clever. Great. So let's check. If the sentence is false, then it must be provable, right? Because the sentence says of itself that it is unprovable. So if it's false, then it must be provable. But now every provable sentence is true. That's the way we set up our proof system. So if the sentence is false, then it must be true. So it cannot be false. Therefore, the sentence must be true. Now, since the sentence is true, it's unprovable, right? That's exactly what it says about itself. And therefore, we have constructed a true but unprovable sentence in number theory. And what Gödel did is he showed that we can come up with a similar sentence for any given consistent set of axioms. So in other words, there cannot be a complete system for mathematics. And this result rocked the foundations of mathematics and shattered the dream of generations of mathematicians who hoped that one day every mathematical sentence can be either proved or disproved. And while the mathematical correctness of Gödel's result was immediately accepted by his peers, its philosophical consequences remain an open and much debated topic in the philosophy of mathematics to date. So does Gödel's result really show that mathematics is fundamentally incomplete? And can mathematics really not prove its own consistency? And at this point, my research enters. And basically, I argue that even the most general versions of Gödel's result, which are known in the literature to date, are not sufficient to settle these questions. And the reason for that is that Gödel's coding apparatus really depends on a lot of technical and arbitrary design choices, while there are infinitely many equally adequate alternatives to choose from, right? So we have here, for instance, different Gödel machines, and they all translate the very same proof to different numbers. So I argue that only if we can prove that Gödel's result does not fail if we tweak some buttons and screws in his machine, or if we come up with an entirely new blueprint of such a machine. In other words, if we employ a different Gödel coding, only then can we really conclude that mathematics is incomplete. So in order to justify our philosophical consequence that mathematics is incomplete, we have to prove that Gödel's theorem holds for all Gödel codings. But now we are faced with a similar challenge as before, and that is that Gödel codings are not mathematical objects. So here the challenge is to use mathematics not only to speak about numbers and geometrical objects and about mathematical statements and proofs, but also to use mathematics to speak about Gödel codings which translate these proofs into numbers. And in order to overcome this challenge, I developed a theory of Gödel codings by using tools from mathematics, from computer science, but also from philosophy. And then using this theory, I managed to show that we can actually indeed prove that Gödel's theorem holds for all Gödel codings. And thereby we can defend Gödel's claim, namely that mathematics is fundamentally incomplete. And then I soon realized that we can use this theory of Gödel codings to also study the limitations of our computational models and our mathematical languages. So we can study what are the limits of what we can calculate using a computer, given infinitely many time and space, and what kind of are the limits of what kind of concepts and ideas we can express using our mathematical languages. And in doing so, I hope to contribute a better understanding of the nature of mathematics and its ability to model reality. Thank you very much.